This video contains a visual description of the best time to sell stock problem. So the way it works is you have an array for the ith element, and that's the given stock on any given day. You are only allowed to make one transaction, meaning you can only buy and sell one share of the stock to find the maximum profit. The crucial thing is you cannot sell a stock before you buy one, which makes sense, but we have to consider it in the context of the problem. So if I just had 7 and 1, I couldn't buy tomorrow and sell today. We don't have a time machine. So what's going on here is that I have an output of 5. So why is that? So on day 2, I have 1, and I can wait until day 5 to sell at 6. So 6 minus 1 equals 5. Here, in solution 2, it's 0 because the stock constantly decreases. So therefore, we cannot make a profit. So when you're approaching these kind of problems in an interview environment, or you're writing one for my class, the first thing to do is think about a brute force solution. So you're taking what you've learned in Fundamentals of Computing or Introduction to Computing Programming and trying to come up with something that actually obtains the solution. So in this piece of code that I've provided here, what's actually going on is I'm actually comparing bit by bit. So I have 7, 1, 5, 3, 6, and 4. And it goes through 2 for loops. So the first for loop is going to be at 7, and then it's going to be at iter plus 1. So the next one's going to be here. And it's going to keep incrementing. So it's going to see 7 minus 1 is less than 0. Then it increments to 5. Then it increments to 3, then 6, and then 4. So we know if we're just comparing those values, we can't find a solution. So then we go to the next iter, and that moves here. Then jitter becomes iter plus 1, it starts here. 5 minus 1 is 4, 5 minus 3 is 2, 6 minus 1, is 5. 4 minus 1 is 3, so we have a current max solution of 5. And we keep going through this in the same way. We keep iterating, we move iter here, we have jitter perform all these, and so on. And so what I showed next, after the code, is all of the iterations. So you can see what I did in all these instances. So what happens is I had iter and jitter. So here's iter, they're all the same. And there's jitter, so it becomes 1, 5, 3, 6, and 4. And then I did the same thing in the second iteration, except I moved 1, it was the new iter. So you compare these here. 1 is the new iter, and it goes jitter is 5, 6, 3, and 4, and so on. And so I described that it takes 15 calculations. We're going to learn later in this semester that this is big O of n squared time. So that's known as quadratic. It's a lot of calculations. So what I said next is we should break this down into subsolutions. So if I say 7, 0, since there's no second date to buy anything. 7 and 1 should also be 0 because I can't make a profit. 7, 1, and 5, I can make a profit of 4. 7, 1, 5, and 3 is a profit of 4. 7, 1, 5, and 3, and 6 is a profit of 5. And this last one is also a profit of 5. And so this pattern that I'm looking at, do you see the pattern with the subsolutions, is that it's always increasing. So we did the same thing where I added multiple minimums, 1 and 0. And so then I went through the same thing where I developed this pattern where 7 by itself had a solution of 0, 1, there's no profit, 5, I can make a profit of 4, 3, I can make a maximum profit of 4, 0, it's still 4, right? Then I add 7, well 0 to 7 is 7, I put 6, it's still 7, and 4, it's still 7. So we see that there is a pattern of increasing. So the question becomes, how can I take advantage of that to significantly reduce the number of calculations? And so what I did in my solution here And this is what I have in this code. So what I do is I have a function, stonks, that calls a vector by reference. So we're reducing the memory. If you look at the lead code, you'll actually see that it maintains the same thing where we have it called by reference. So what I've done here is I have a solution, and then I have a global minimum that is higher than any of the values. So you could set that as the largest possible value that could be stored in a global minimum. And the reason why we want it to be that high is because I'm going to iterate through each element. Now notice how I'm only iterating through once. I'm not going through each element and then going through each element there. That allows me to take it from quadratic time down to linear time. And so what's happening is I start out and I say, well, if the vector is at that location is less than the global minimum, then I set the new global minimum equal to that value. Otherwise, I may have an opportunity for a potential solution. So if the vector at that location minus the global minimum is greater than the solution, then we set the solution equal to that value. And at the end, we return the solution. So what's going to happen is I have it written out here, all these steps here for 7, 1, 5, 3, 6, and 4. These are the steps. I want to go through 7, 1, 5, 3, 0, 7, 6, 4 and compare it to this code. 7, 1, 5, 3, I think it's 0, 7, 6, 4. 3, 0, 7, 6, 4, that's correct. 0, 7, 6, and 4. So here's what we're going to do. At this point, I'm going to write out what solution is and the global min is. So I go through the first iterator. I see here that 7 is less than global min, so solution remains 0, but now global min is going to be 7. We go through the next thing. We see that the vec that 1 is less than 7, so solution remains 0, and now our global minimum is 1. Now we're going through the same thing. 5 is greater than the global minimum, but now we have if the vec dot at iter, which is 5, minus 1 is greater than the solution, so that's 0. So now we have 4, and our global minimum is still 1. We go back through, we see 3 is greater than 1, and 3 minus 1 is 2, which is less than 4. So our subsolutions continue to propagate. Now we're at 0, and 0 is less than the global minimum. So the solution remains the same at 4, but now we have a global minimum, so anything to the right is a potential solution. Next, we are going to say that 7 is obviously greater than the global minimum, but we have 7 minus 0, not 7 minus 1. So now we have a 7, and our global minimum remains at 0. When we do 6, we do the same steps, but now we get 6 minus 0. So that doesn't meet that if condition, so 7 remains. And finally, the same thing happens with 4. So I am, in main, running several tests. I expect this one to be 5 because it's 6 minus 1. Here I expect this one to be 0 because it's constantly decreasing. Here I expect this one to be 7 because of that's the test that we just ran. And finally, I created my own test that's constantly increasing. We know this will work because the global minimum always remains 1, and each time it gets updated. So the subsolutions become So now let's run it and see what our results should be. And when I run it, we get 5, which is what we expected, 0, which is what we expected, 7, which is what we expected, and 6, which is also what we expected.